So, good morning, everybody, and today we are going to discuss our first channel model we have studied last lecture, ideal channels with band limited frequency response. So, today we are going to design a program in Octave that can simulate such channel, but before that we will cover how we model this channel as a filter. What are, let us say so, response parameters, and basically how do we calculate such a filter, because there are multiple possible parameters and we have to understand what each of these parameters actually is influencing. We will here and then return in some ways to our previous lecture when it will be relevant, yes. So I will show you everything during this lecture. And also I'm adding this Teams link, yes. So basically each time we start a new lecture, you will see this meeting link, yes. This meeting link is different for each lecture. So once this lecture ends, I'm going to erase it. And once we start new meeting, I will add accordingly link, well, on the third lecture, fourth, and so forth. So yes, about practical exercise, what we are going to have today. Currently, no individual parameters have been yet put here in Ortus, as you can see, but after this short lecture, I'm going to add one more file here that will contain some individual parameters you will need to finish this practical exercise. So at the beginning, I was planning that this is today's lecture. At the beginning, I was planning that we would actually make all these models at one practical exercise and compare them. However, when I tried to implement this ideal channel model, I found it already to be quite complicated to be a separate practical exercise. Now, of course, adding noise is not that difficult, but making unknown phase again will probably ask from us an additional time. Yes, that will be enough to make a second practical exercise and so forth. So basically, I decided that there is no need to give you so much material in so short time, because otherwise you might be scared and maybe not even join this course ever again. So I decided that we will take it slowly, yes, and in fact I don't even know how proficient you are in MATLAB or Octave programming, whether you had some digital signal processing course or not. Are you familiar with filters, how to, for example, determine its responses, frequency response, and impulse response. So everything will be covered on this practical exercise step by step. Also, it will provide you useful commands to plot different types of plots. So that is going to be our today's topic, yes. So as for the time schedule of today, we are going to spend roughly 1 hour for lecture part and then up to 2 hours for the practical exercise. Well, I believe that most of the parts we will do in the first hour, and then I will show you some additional things, not maybe really necessary to prepare your report, but just to show you the difference when channel is not really ideal, what can happen in that case. Yes, and well, I hope that we finish everything today in time. Yes, so we have roughly around 3 hours, and we will have break each hour. Yes, so basically once 1 hour passes, then we will have some break, then again 1 hour for practical exercise, a break, and finish our practical exercise. But if we finish faster than 3 hours, it's okay. So that means you will have more time for other matters today. So let us start with today's lecture. Last time we have basically briefly described each of these models, and today we are going to spend a little bit more time about this ideal channel and its responses. So, to recap our last lecture, we have specified it as this mathematical, how to say it, expression, yes, as this mathematical expression, as this model of the channel. However, we need to actually consider this limited channel bandwidth, yes, because it's not really that simple as it's written here, because currently this only makes some time delay and attenuation, but in no way changes the shape of the signal. Of course, this limited channel bandwidth effect will change the shape of the signal. And today we are going to discuss how exactly. We did mention amplitude frequency response, phase frequency response, and today we are going to see how this response should look like for something attainable for ideal channel, something that we can actually design in real world. Yes. So let us start with the, okay, I didn't mean to actually close it. Let us start with basics, how this ideal channel should, this ideal channel frequency response should look like. So basically, what was shown here is not really that ideal channel. For completely ideal channel, we would have this type of amplitude frequency response. So it will be a so-called brick shape, rectangular completely, yes. And for the phase frequency shift kink, this is going to be a linear function. We already discussed that this will provide a constant time delay last lecture, yes. But today you are going to see why is this so important. So, and then for ideal frequency response, we are having this bandwidth set to some specific value. Yes, basically for each communication system, we always have this limited bandwidth set by some standard. For example, 80 megahertz for Wi-Fi networks, or 20 megahertz maybe for some LTE mode. In some other LTE mode, we might have more, we might have less. It is dynamically distributed depending on demand of the user, yes, but it's around 5 to 20 megahertz, let us say so, yes. So this is some channel bandwidth, yes, and there are multiple such channels in most of the system. So we have to, how to say it, separate these signals in frequency domain one from another by making according attenuations. You already know from the bachelor course that most of the signals have, let us say so, infinite spectrum width. Yes, so basically some kind of spectrum that's theoretically is asymptotically close to zero, but never really reaches zero. Yes, however, the values often degrade very fast. Yes, so for example, for rectangular shape pulses, we have sinc type function, and basically we already can set a limit somewhere around here. That is 1 divided by tau. No, by 1 divided by tau, which is tau the length of the rectangular pulse. So, of course, after such filtering, the pulse will no longer be completely rectangular. here you need to actually consider whether we are talking about frequency domain on the x-axis or time domain. In this picture up here, we are having time here and frequency here. So basically, as you know, Fourier transform can convert a signal from time domain to frequency domain. And it works vice versa as well. So if we have this frequency domain representation of the signal, we can use inverse Fourier transform to actually get the shape of signal. In that case, this automatically solves the question, what kind of signal is valid for such case? Yes, so what kind of signal will have this strictly brick shape, strictly rectangular spectrum bandwidth? Yes, so, and it turns out that the signal itself will have to be the sinc function, because Fourier transform is also, how to say it, dual in its nature, right? It's meaning that the same shape of signal in time domain can be obtained for the frequency domain and vice versa. So if, for example, in time domain we have rectangular shape, then spectrum will be sinc function, sin x divided by x type function. And vice versa. If we have signal of the shape sinc, then its spectrum, its Fourier transform will be rectangularly shaped, right? So that means that the signal we are going to use that will have this limited bandwidth is going to be a perfect sin x divided by x type function. However, this is not really physically possible to implement because of multiple factors. First of all, we will never get the filter with that steep cut-off frequencies. So basically, we can say that this is actually some cut-off frequency of our filter. And sadly, we cannot design such filters with so strict cut-off frequencies. It will always have some transition band like this, when amplitude will decrease slowly, not with a single step, right? For some band, yes, for some frequency range. And because of that, this is not going to be a completely rectangular shape, and accordingly, the signal will not be a complete sin x divided by x function. But we'll get to that in a moment. Right now, I would also like to mention that it is possible to calculate some low frequency equivalent signal. We will not do it right now, but we will return to that a bit later. That has the same bandwidth as our, let us say so, modulated signal. So here we are going to talk about some signal on carrier frequency of 0. Thus, that means we have some modulated signal, right? And accordingly, as you know, Fourier transform property allows you to make the shifting of the spectrum or the signal in time or in frequency accordingly, right? So it's quite possible to find a low frequency signal. Basically, this is called, the process of it is called demodulation, right? With equivalent bandwidth. So as I said, for ideal case, for perfectly band limited signal, we have this brick shape amplitude frequency response. And for the phase frequency response, as we already mentioned that earlier, it's going to be a linear function. So in complex form, this frequency response can be written as exponential form of a complex number, where we have absolute value, that is our amplitude, and we have argument as the power of complex exponential e. Yes, so that is the argument or angle. That's what we discussed last lecture in a lot of details, right? Right here, that we have amplitude response and we have phase response. And also we mentioned that there is also a group delay time, which is in fact a derivative of the phase response. So if the phase response is actually a linear function, then derivative of that linear is going to be a constant, which means that signal is, how to say, all components of the signal are delayed by the same amount of time. That is very important for correct reception of the signal, as you will see from today's practical exercise. And what matters the most is if we have linear phase, then this is achieved automatically. So that's a quite, how to say it, important requirement for ideal non-distortive channel. So let us once again recap the requirements for ideal channel. So the absolute value or amplitude must be constant in all frequency range. Yes, so basically if we have this delta F frequency range, even slight decrease will make some distortion of the signal, which may be a tolerable level, but nonetheless, this channel is not like completely ideal in that case. Sadly, real filters will always be like that. Yes. Next, phase frequency response must be a linear function. Again, this is not always true, especially for continuous time filters, right? Where we have non-linear phase. I don't know how much of the filters do you know currently, but today during our practical exercise, the second part, we will talk about some examples, and it's well, in short words, I can say that this is a case of so-called infinite impulse response filters. Infinite impulse response filters. So that means that, well, actually, let us then start from the very beginning. What is this impulse response actually? Yes, so basically we have some kind of filter and we want to know its impulse response. As it comes out from the name, this is the response of this filter for the how to say it, input signal shaped by a single pulse. Yeah, so at the input we have this impulse at the time moment t equals 0, and then at the output we are going to have some response to this. So you can imagine it as hitting some small bell with single strike and hearing some sound generated by this bell for some duration, which slowly fades off, right? So in the same way, this works for electrical filters, and for the infinite impulse response, this response is theoretically infinitely long. Yes, it decays to 0 quite fast and never really reaches this 0 completely, but it's, well, at least in theory, infinitely long. This is achieved by using some loopback. So the structure of this filter will look somehow like this. We have direct part and we have this feedback part, right? So that means if you generate this one at least once at the input, then this one will never really exit this loop. So the simplest example can be shown as this. Yes, we have this multiplier of 1, half, right? Then we have this delay unit. Now I'm talking about digital filter, but digital filters can also be with infinite impulse response, as you will see right now. And, well, actually this is z minus 1, yes. And now if we send at the input signal 1 and then infinite amount of zeros, we are going to have at the output in the first time moment. Well, actually, let us put it in another place here, so that the first output is going to be 1. Yes, and that means we have to put it here. Here, like this. Right? So if the input is 1, the output is also 1. And here we have addition. So we add signals here. Like this, right? So at the input 1, this 1 is set to the output and also recorded inside of this memory cell as 1/2. Now, previously here we had 0, so 1 plus 0 gave this 1. Now, next input is 0 and the memory contains 1/2, so we are going to have at the output 1/2, and then this same 1/2 will go to this memory cell again, and it will be contained as 1/4, right? And this will never end. Each time output will be twice smaller, but it will never reach actually 0. It will be infinitely small number, but not 0, right? So that is infinite impulse response filter. And we cannot really, what is important here, we cannot really make this, how to say it, linear phase frequency response that easily for such case. So it's quite difficult task to make this linear function of the phase frequency response for such type of filters. Now there is also type of filters called finite impulse response. These can be only digital filters, right? And in fact, it's quite easy to achieve this linear function for such filter. So we'll talk about that more in practical exercise when we are going to actually calculate this filter, and maybe even during the lecture when you will know how the ideal channel impulse response should look like. So what's important here, if at least one of these conditions is not met, well, actually these two are related, so it's impossible to get this as a constant if the function is not linear. Yeah, so basically this is the same condition. So basically that would be condition number 2, and this would be condition number 1. Then transmitted signal will have some distortions. Much or less, this greatly depends on what type of condition is not really met, for amplitude or for phase frequency response. In both cases, again, it also depends on how severely we are far from this ideal case. So, as I said, for ideal limited frequency range, for ideal bricked sized bandwidth, right? According to Fourier transform, the signal should look like this. So basically, this is called sinc type function, sinus x divided by x, right? And this is infinitely long. So again, this will continue up to infinity. It will become smaller and smaller, but it never really reaches 0. That is first reason why we cannot really make such filters, right? Such signal, because it's impossible to generate this signal that was somewhere infinite time ago, right? So basically what we can do is to start generate signal now at the time moment 0. And here it's out of our, I would say, control to actually generate that signal. Yes, that is the first reason. The second reason is that this is the response of the filter with such amplitude frequency response. And as I said earlier, we cannot design a filter with such amplitude response, well, unless it is very, very complex, infinitely complex, right? And again, as if it is infinitely complex, then we cannot really make one. So we might be very close to this response, but it's not completely rectangular. Yes, because all these strict rectangular angles require quite a large number of how say it, components in the Fourier series, right? And for that reason, it's often not really practical thing to do at the beginning, right? So we know that theoretically this should look like this poles should look like this. So that means that actually, if we in any way succeed in making such a filter, right? Let us assume that we have this filter right now. Then sending these pulse at the input will produce us the infinitely long impulse response of the type sin x divided by x. Now, what is so good about this type of impulse response? The good thing is that if we send a next symbol after some time interval, then it will hit straight at the moment when here we have 0. As you can see here at the 1, 2, 3, 4, 5, at integer numbered normalized time intervals, right? We have normalization made by time divided by sampling. Not sampling, but symbol time, test symbol. Right? So basically, this is the first symbol, the second symbol, third symbol we transmit, and so forth. And each symbol doesn't interfere with previous at these specific time moments. It's, of course, worth to note that between the symbols, we will have some interference, but what matters the most is that this symbol will produce 0 interference to other symbols that will follow next. So that's why this function is really very desired for us. Yes. So, but as I said, it's not really practically possible to achieve, right? So we have to, how to say it, find some alternative, some way to replace it. So we'll talk about that right now. But before that, let us see how this can add up together by sending multiple symbols at the same time. Not really the same time, at different time intervals. So here you can see that we send black colored pulse at the time moment 2, -2, and this produces this impulse response. So instead of sending this, let us name it delta function, right? This really short time duration pulse, we are going to have this entire function that will last quite long. Theoretically, of course, infinite time, but even in practical consideration, it will still be long enough to actually affect multiple next symbols. Now, as I said, since we have this sync function, it will have 0 contribution at the time of the next pulse, which is here denoted with green line. So here we have the second data pulse, right? That also produces this type of function that will also overlap with the previous one, right? So in fact, what we are going to receive here is going to be the sum of all these pulses. Now what I'd like to mention, that at least from theory, it also affects previous symbols, right? So in this particular case, this negative direction means that in fact, when we were sending these pulses, we were actually considering the future symbols as well. Now, as you know, in practice, this is also not really, how to say it, achievable, right? We cannot know for sure what symbols are going to be sent in some kind of future. Now, we can, of course, collect some symbols and then it will be relative in future, right? But that's about it, how far we can get. So, in short, the total signal is, which is actually this low frequency equivalent of our radio signal, is going to be the summation, addition of all the data pulses sent. Yes, so basically these are our data pulses multiplied with impulse response of our ideal filter. Yes, idealized filter, which again I'd like to mention is not possible to make one. Now, so as I said, if we make some filter that in any way is not really that ideal, right? As you can see, for example, here, it's not really zero value at next symbol time. Here we have non-zero value. Then we are going to have slight interference. Now, this is not really much compared to the next symbol, but it may still add up considering the fact that we are going to have multiple such symbols. Yes, for example, for this last symbol, we will have this black colored contribution, we will have the green colored contribution here, we will have blue colored contribution, and a red colored contribution, right? So all of these previous symbols will equally contribute and basically decrease the value of our pulse. Yes, so this will make distortion to our actual next symbol. That is, if we fail to make such a filter, that is not ideal. So at this step, we might say that, well, unfortunately, we cannot really do what we want and it's impossible. However, we don't really want to have completely ideal sync function. Yes. Well, at least, how to say it, we can still be close enough to desired result even without ideal function, right? If we make some simplifications and assumptions. We will talk about them right now. But before that, what I'd like to mention is that in fact what we are going to see instead of this is going to be addition of all this line, and this addition will produce this kind of line, right? So in fact, for some points, we might actually even, how to say it, overshoot the value of our pulses. But nonetheless, if the filter is designed correctly, then we can still simply read the blue line and we will receive correct values of our original signal. So here you can see red lines of the original signal and blue line how the signal will look like after passing through our filter. And in fact, today in practical exercise, we are going exactly make such experiment, right? With the signal composed from your name, surname, letters, represented by either +1 or -1 value, and accordingly you will also have some filter parameters which you will need to take into consideration to actually make this model, right? So this is what we want to do. Now, how to do that? We need to use a so-called pulse shaping filter. Now, in fact, we are going to have one filter in transmitter and one filter in receiver. But for simplicity case, today we are going to merge them into a single filter, right? So instead of that, we are going to make this diagram that we have transmitter, we have this channel, and we have receiver. And this channel filter consists of these two parts. So this goes here and this goes here, right? And right now I'd like to talk about how these two filters will look like, how to say it, together, right? Their total response. Well, as you imagine, ideally we would like to have this sync type function represented accordingly with the sin of the time divided by time. Now it's not really achievable, but we can make quite similar ones. Yes, in fact, they will also be sync type, but their argument will not be time, right? That will be some additional coefficients, some parameters, and basically not exactly there, but some more. Yes. Now we can see additional materials by following link in this presentation. Yes. In fact, I use some pictures from here as well. But what's the most important part is that we no longer want a completely rectangular shape, right? So as you can see here, it's okay to have some round edges, and that kind of thing is achievable in practical exercises by making this kind of function like it's mentioned here. Yes, and in fact, if we set some specific parameter called beta that actually defines this roll-off factor, how round is this edge, we can set it to 0 and achieve completely rectangular shape in theory. Again, of course, in practice, it will not work like that. Yes, it will have some undesired effects, not really expected from theory, but at least this model is adequate, that it includes this ideal Nyquist filter. So that what is ideal filter is called a Nyquist filter, right? I didn't mention that before, but right now we are going to mention it. Well, basically, you can use this, how to say, material. It also contains some more material here with the link, right? Let's see if it's working. Well, sadly, this link is no longer working. These are some material for lab, but well, there is no really some task in this lab. Yes, it's not really said what you need to do here, because well, I found this material somewhere on the internet. It's not really my lab task. Yes, so okay, let's continue. So as I said, there is an entire family of such filters, and one of them is this ideal Nyquist filter. Not really achievable in theory, but still a part of this family. Now, next one is raised cosine filter. This is what you have seen in those pictures which I showed right now, and square root of the raised cosine filter, which is basically the same, except we have a square root of this response. Yes, we will talk about why we need to do that soon. But right now, let us see what is this Nyquist filter and what is raised cosine filter and how close we are with the raised cosine filter. So our channel in that case is considered to be this filter, right, with some specific response, and then it converts our pulse into these responses, right? So yes, as I said, Nyquist pulses are completely ideal, but not really practically achievable, right? So Fourier transform does mathematically connect these two pictures, right? So if you use as a spectrum this picture, then by using inverse Fourier transform as a signal, you will get this sinc function. This is, how to say it, defined by this Fourier transform. Now, here you can see some more additional material. Now, I don't really remember. Yes, this is about, yes, how to say it, intersymbol interference, right? How it's happening. Yes, how it's happening if this channel is not really meeting this requirement of this ideal response, right? So for ideal case, we have zero overlapping at these sampling time intervals. Now, however, if we have not really ideal, no, wait a minute, where was that? So intersymbol interference. It's not really here. So there is no pictures here how it will look if we have this intersymbol interference. But you already should understand from my previous examples that it will mean that each of these will not be completely zeros at these time samplings for this line, right? And accordingly, this will have some contribution that will interfere with next symbols. So, okay then. But as I said, this is not really achievable. So what the best thing we can use that is very similar to this Nyquist filter is so-called raised cosine filter. Well, it's called raised cosine filter just because its mathematical expression is actually this type of function like cosine of some x plus some constant. So basically that means that this cosine function, which normally looks like this, centered around 0, is actually shifted up, and now we have it like this. Right? So this is called raised cosine, and basically that's how these filters came to have this name. Now, the difference with the Nyquist filter is in small details, right? So it's going to have wider required bandwidth. So nonetheless, if we look at the impulse response of this cosine filter for different beta parameter values, you will see that it actually can have zero contribution at the sampling intervals, right? So basically when our symbols come, all of them are actually zeros, regardless of the beta parameter. Now, another important thing you can mention from the picture is that actually the greater is this beta value, the smaller are these ripples, right? So for example, let's see for beta equal to 1. Okay. So these oscillations have really small amplitude compared to beta equal to 0, right? That's another important thing. And thus, it will also have less, how to say it, less interference in points between the symbols. Now, it may not be really important from theoretical point of view that what happens in between, but for practical systems, considering that channel does have some memory effects, this might actually be beneficial for us, right? So you can read more about raised cosine filters even in Wikipedia, right? So here you can see also mathematical expressions, how impulse response will look like. This exactly same picture I have shown you right now. How frequency response pictures will look like. Yes. And what is this actually beta parameter? It is excess bandwidth factor, right? So basically, according to Nyquist filter, we have some minimum required bandwidth that we have to use. So this is shown here with blue line, right? So this is our delta F minimum. Now, if we have beta equal to 0, then we have 0 excess compared to this. So that is excess, yes. Compared to this original end, we have delta F equal to this delta F minimum. Now, once we increase this beta, we are actually having more bandwidth than is necessary according to theory, more and more, up to, for example, even making it twice as large. So this is basically 2 delta F minimum, double of minimal, yes. And beta is actually the ratio of this difference, right? Basically, this difference related to this delta F minimum. So this is, how to say it, this is for entire channel bandwidth, which can be set as delta F minimum, which is this original theoretical bandwidth, plus some delta, yes, which is happening to be in this particular case also equal to delta F minimum. And then beta can be calculated as this difference delta divided by what is really necessary, right? So in double exceeding case, we have this beta equal to 1. Yes, and you can easily see that indeed, when we have beta equal to 1, what we have here is actually twice as great bandwidth compared to what we have when beta is equal to 0, right? Now, this means that we will have to provide twice as large frequency bandwidth for this signal, which will effectively reduce number of users if we have limited total range of the frequencies, but will at the same time reduce also the effect of these symbols to neighbor symbols, right? So in practical exercise, you will have each of you different value for this beta parameter, and you are welcome to compare your pictures by exchanging them between yourself, right, and your group members, and in this way you will see for yourself this effect, right? You can also always change it manually in your own program to see how it will work if we change this value. Now, we can even write this mathematical expression for this raised cosine filter impulse response, right? So basically, this is the formula in general case for this picture, right? So according to different beta values, you are going to get either one of these lines. Now, in this picture, you can see that we have this cosine, which is actually this raised cosine function, and sinc function, how to say it, window function, right? So, in fact, this is our ideal Nyquist function, right? So this is Nyquist function. And this Nyquist function is multiplied with the cosine function. So basically, this way we have these round edges of the spectrum of our signal. Now, in some particular case, when time is equal to plus minus t divided by double beta, yes, which is specific case, right? We have this formula a little bit different. So how it came to be? Let us see what is actually going to be t divided by t capital if t is equal to this number. So we are going to substitute it here and get this type, right? So it's going to be 1 divided by double beta, which accordingly converts this into this, right? As for this part, it's a little bit more, well, so far it's no really reason to see why this is so special case. But in fact, this is more important here when we will calculate this square. And that's why we have here both plus and minus, yes? Because this expression, when t is equal to t capital divided by double beta, is actually going to be like this. Right? And accordingly, it will be reduced to 1. Now, this 1 minus 1 will produce 0. And we have here division with a 0, which is a problem for computers, right? So in that particular case, when that happens, we have to calculate according to this formula, right? So that's why there is such additional case. But we will do that today in code by making this condition and implementing this formula for these conditions in a specific way. So basically what we are going to do is just make this second formula. Yes, basically like this. And then for some specific points, which will be 2 of the points, right, we will update result with these 2 values. So I will show you how to do that in Octave, and it will be fine. Now, for the frequency response, we have this kind of expression, which is actually raised cosine. You can see it here. We have cosine function here. Yes, it has a lot of parameters in brackets, but it is still a cosine. And here we have this cosine raised by the value of 1. So originally cosine is in range of -1 to +1. Then after this addition, we will have this cosine in range from 0 to 2. Now, in order to get it back to the maximum possible value of 1, we have this normalizing factor, right? So it will be after that in range from 0 to 1. Now, that is only true for this range of the frequencies. That is actually our delta F, our desired frequency range. And you can see it here. Yes, actually this is, well, this is pure cosine function, right? So if we make here at 0.5 this central line, then here that is actually cosine. Yes, it's starting at the maximum, and then it would continue like this if we would allow it to. But we don't calculate further than that. Yes, so basically it's okay. Now, in order to prevent this further increase as normal cosine would do, right? We set it to zeros outside of that range. Now here we have this specific range when our function is equal to 1 strictly, but this is quite short range here, right? For some short range here it is 1. It depends on beta parameter. So for example, if our beta is equal to 1, then actually this range is going to be 0 at all, right? So beta equal to 1, 1 minus 1 produces 0. So there is no such range. It's better seen here with the green line when we have small beta value 0.25. So here we have this cosine part, then we have this part of the constant level, and then we have again a cosine part, and then 0. So we have these 3, or in this particular case, okay, 5 pieces of the function, right? So it's given by piece wave formula. But the most important part here is this, right? So we can calculate it according to this function, and then in missing positions we can replace the missing values. So if we calculate that in octave. Now sometimes we want to calculate this function, sometimes we want to calculate this function. But also please remember that we still have Fourier transform at our disposal, so that can produce us Fourier one from another. For example, if we use the impulse response, then as a result we would get this frequency response. And that's how it may be even easier to design this filter, because we can use this Fourier transform, we can use Z transform as well to generate a digital filter, right? With this desired frequency response. And it will be convenient for us when we talk about root square of the raised cosine filter. So the last few slides before our break about what is different about square root cosine filter. Now, as I said, we usually separate this filter between two parts. One part is put into transmitter, and it's called pulse shaping filter, that actually generates the specific form of the output signal before modulation, and then accordingly it's being transmitted. And then in receiver we have a matched filter, which is accordingly, how to say it, supplementing or adding, so that their merged frequency response is one of the raised cosine. So this raised cosine response is split in two parts. One is put in transmitter, another is put into receiver. And basically these two particular parts in their multiplication have to produce the frequency response of the raised cosine filter, right? So what is the easiest way to split it into even parts so that their multiplication is going to be this raised cosine? Well, that's correct. Actually, we have to make square root, right? multiplied with the square root, that will accordingly produce us this original one. So this is going to be, for example, transmitter. This is going to be receiver. They are exactly the same, right? So each of them is square root of the total one. And accordingly, we put one into receiver, we put one into transmitter. It doesn't even really matter at this point which one goes where because they're identical, right? And in general, when we use both of them, we get this response of the raised cosine filter or Nyquist. So if it could be completely ideal, right? So what matters the most in this situation is that we no longer have to provide zero interference at these moments, yes, when we have next symbol. So here, for example, is symbol number 1. Here we have symbol number 2, and you can clearly see that each of these lines is not 0, right? And it doesn't even matter for us. If it is 0 or if it is not 0, it will be fine in the end once we apply the second filter. So keep in mind that this is only first filter. Once we have the signal filtered again with the same filter, we will have no problems, right? So yes, what's important to mention here, we have no zeros, right, in the reading time intervals. This will accordingly produce interference. Yes, intersymbol interference, and that's how it's looking. So I believe these pictures have been taken from Bernard Sklar book. You can see more text about it in there, and it's clearly shown here that we have 0 here, we have 0 here, and our impulse response doesn't really actually hit these points, right? As a fact, as a consequence of this fact, yes, once we send our data, for example, +1, +1, -3, +3, +1, +3, through this filter, you can see that the line generated by the output of the channel doesn't go through our original points. Yes, so that is a problem. If we read these points directly from this line, then we would get this value here, well, something close to what really was here, even more than needed here, right? Here, close to what we need to have. But in this particular case, you can see that we lost quite a lot in this symbol, right? So we risk to read it incorrectly because of this interference effect. Now, if we filter this, so basically what is shown here in the picture is basically HRX. So basically here we have inputs. Oh, sorry, -3, +3, +1, and +3. So we have as inputs this signal and as output this signal, right? Accordingly, what we are going to do next is now filter it with the transmitter. Sorry, this was transmitter part. And filter it with receiver part. This signal goes then through this filter, and as a result, it all smooths out, right? You can see that now each point is on this line, and accordingly, there is no more intersymbol interference. Now, we will return to this fact when we'll talk about channel equalizers, because currently we are talking about our communications equipment, of the filters we are using in our equipment to actually prevent interference between different channels. Because if we wouldn't put these filters, then what would happen? If we don't put these filters, then we have channel 1, for example, specified for one user, channel 2 for second user, And without this filter, the spectrum of our signal would interfere with the second user and will make disturbances. It will make, well, not really noise, but interference to that channel, and the second user will not be able to use this channel. So we have to use filter to limit our bandwidth so that we generate zero interference to other users. And other users also have to use their filter, right? But because we use this filter, we risk to have inter-symbols interference for our own signal. In order to avoid that, we have to design very specific filter pair, right? So, in fact, this solution of the square root cosine is not a, how to say, only one possible solution. We can actually generate different filters here, but as long as together they provide us this raised cosine filter, right, we are fine. So we need to make sure that their serial connection of these two filters will produce this frequency, this impulse response, right? Well, and in fact, for the impulse response of such a filter, the mathematical expression is like this. Yes, so for 0 time interval, we have this formula. Well, basically, again, this happens because if we set it to 0, right, here, then we'll have 0 here, we'll have 0 here, and 0 here, right? So basically, it's going to be 0 divided by 0. And this kind of uncertainty is not that easy to calculate. So for that reason, what I believe here we can see is actually probably just simplified version. Yes. It depends on beta also, and it's basically this maximum value. As you can see, this maximum value for different beta values is different, right? Now, the rest is accordingly this function itself, except for some specific moments when we again have this equal to 1, and therefore this is not 1 nominator, right? And therefore we get some number divided by 0 not really uncertainty, but error in calculations of the computer, right? So for that reason, in these particular points when we have this as 0, and there are only 2 of such points, right, with plus and with minus sign, we use this particular formula to calculate those points. Otherwise, we stick to this formula. So that is for theoretical part. Now, after a break, we are going to I'm going to show you. Yes, so we are going to open Octave. You are welcome to open Octave as well, and we are going to step by step make this filter, make this model, and see how it distorts or doesn't distort our input signal, right? So, are there any questions about lecture material so far?
Sir, can we use MATLAB for the implementation or only Octa?
Yes, you can use MATLAB as well. They are completely same here because we don't use any, how to say it, any special functions. Yes, we are going to use just basic MATLAB language.
Okay, thank you.
So, okay, let us make a break of 20 minutes around, yes, so that I can test each of your parameters and it will not have any errors. So in 20 minutes, we are going to have our practical exercise. Until then, you are free to disconnect and reconnect later at that time. Yes, so thank you and see you in 20 minutes.